We know there are supermassive black holes at the hearts of most galaxies, and these can have millions or even billions of times the mass of the sun. And the big question is, how do they get so big? And thanks to JWST, we're now seeing these supermassive black holes earlier and earlier in the universe. Now, we know that stellar mass black holes merge, and so it seems obvious that supermassive black holes merge, but there's a problem of scale, and that is that it takes a lot of energy to slow down the motion of a supermassive black hole. A way to be able to get two supermassive black holes to merge with one another. This is known as the final Parsec problem, where you can have black holes be brought into each other's environment through a galactic merger, but you just don't have a way to slow them down to get them to merge. And yet, thanks to observations with the pulsar timing array, we see the background hum of supermassive black holes merging with one another. So it definitely happens. But how? And this is a really difficult problem that astronomers have been trying to solve. They proposed many different ideas: gravitational slingshots of stars, black holes interacting with gas and dust, gravitational waves releasing energy, causing them to spiral, but none of these really can account for the enormous amount of energy that's required to complete this final parsec amount of merger to bring the black holes together. What about dark matter? So my guest today is Dr. Gonzalo Alonso Álvarez. He's a postdoctoral fellow at the University of Toronto. He's proposing that there are certain aspects of dark matter in the way that it interacts with itself that acts like a brake, a friction source for a supermassive black hole that is moving through it. He thinks that they have detected a faint signal of this friction interaction with supermassive black holes in the pulsar timing array. And this could be the explanation for the final parsec problem. We have a really great conversation just about what the final parsec problem is. So if you sort of weren't entirely sure what it was, now you should have a very deep understanding of why it is such a thorny problem in astrophysics. We talk about the possible ways that dark matter could be solving this problem, and in fact, what this could tell us about dark matter itself. And then we talk a lot just about supermassive black holes and how they're being found so early on in the universe. This is a mystery. Anyway, it's a fascinating interview. I know you're really going to enjoy it. So let's get going with Dr. Gonzalo Alonso Álvarez. Gonzalo, what is the final parsec problem?
Yes, so the final parsec problem has been a long-standing question or problem in astrophysics, because we kind of understand, so by now we kind of know that galaxies at their center hold a supermassive black hole, right? So we're pretty certain we have different kinds of observations and evidence for its existence, but now the question is, how do they actually form and how do they grow to become so massive? And of course, because these black holes live at the center of galaxies, and we kind of know what happens with galaxies. We know that galaxies grow by accreting material around them and also merging with each other. So we kind of think that the same would happen with supermassive black holes. So then the idea is that when two galaxies merge, they collide and merge, we expect that the black holes would also end up merging and such form a larger black hole. And that's one of the main ways that they grow. However, so calculations for the time that it would take those supermassive black holes to actually merge after a galaxy merger show that this time can be as longer than the age of the universe. The main idea being that, for these black holes to actually end up coalescing, they have to lose a lot of energy. They have to slow down a lot. And it's not easy because they're so massive, and it's not clear what could be there slowing them down so that they could merge. So this is the final parsec problem.
And so when we think about merging stellar mass black holes, obviously this is happening. We're seeing them with gravitational wave observatories, and black holes are surprisingly similar from, you can't describe them in very many ways. And so why do stellar mass black holes merge, and there isn't a final parsec problem for that, or I guess a final astronomical unit problem, while there is the parsec problem for the supermassive black holes?
Right. So I agree. So black holes are similar in essence. It's just that the supermassive black holes are really, really way more massive. So when they move around, they really carry way more energy. So they have to lose way more energy before they come close. And it's also a matter of where they start, because astrophysical black holes, they may be formed, say, in globular clusters, so in ambience of very dense, where there are a lot of stars, and they may be already quite close together to begin with. And then plus with, their masses are similar to the mass of the stars that are around them, so they can kind of effectively lose energy when one star passes close to the binary. Whereas supermassive black holes, you need, a lot of stars really passing close by to them, and kind of, the way that they extract energy is that one star comes close to the supermassive black hole, and those kind of gravitational assist, like the maneuvers that spaceships use to accelerate, right? So the star accelerates, and of course, because energy has to be conserved, the black hole slows down. But the black hole is so massive that it barely notices the star passing by. So that's why it's so much harder to extract energy from supermassive black holes.
I mean, obviously, if you had two supermassive black holes on a head-on collision, they would merge, and that wouldn't be a problem. But the chances of that happening are incredibly remote. You've got to have the black holes find one another in the galaxy, and then some kind of three-body interaction needs to get them into orbit around each other. And then, as you said, countless stellar flybys and gas and whatever needs to be moving in the right direction to cause this loss of energy that gets them to spiral inward. What about just gravitational waves? I mean, there must be other mechanisms that are causing the black holes to spiral towards each other.
Yeah, exactly. So gravitational waves is also, when the gravitational waves the supermassive black holes are sufficiently close to each other, they start emitting gravitational waves, and all that energy that's being carried away by the waves is precisely the orbital energy that the black holes need to lose to merge. However, gravitational wave emission is only really effective once the supermassive black holes are very close to each other, like a distance is smaller than a fraction of a parsec. When they are a parsec apart, they still emit gravitational waves, but the emission is so weak that only, like, if they had to lose all their orbital energy through gravitational waves, then it would take many times the age of the universe for them to merge. Right, so there has to be something else that helps them get close enough, and then once they're a fraction of a parsec apart, then gravitational waves can finish the job.
Right. And that is the heart of the problem, which is that if you're going to rely on gravitational assists, loss of energy through gravitational wave emission, you're not going to get those black holes close enough for the age of the universe. And yet when we look out into the universe, we see tons of supermassive black holes that have already found one another and merged. And here we are with things with billions of times the mass of the sun, a billion years after the beginning of the universe. And so that's clearly not the age of the universe. So I can see the dilemma. So what are some of the other common mechanisms that have been proposed as ways that you could overcome this final parsec problem?
Right. So probably the main mechanism is this that we were describing, these stellar flybys that extract energy. However, this is a very hard problem to simulate, because you were saying, because of the huge mass difference between a star and these supermassive black holes, there needs to be a lot of stars that come very close to the black holes, right? And really, knowing how many stars there can be at the center of the galaxies in this, with the right trajectory such that they can close together, is very hard to calculate. So people have been doing a lot of work for many years and simulations and refining their predictions. And what they can say is that it looks like stars are not enough, but still, the results are not as precise as they would like to make a final call on that. So that's still a possibility. Maybe we're missing something in the calculations, maybe that will improve in the future and show that the final parsec problem can be solved just with stars. But that's not where we're at right now.
When I think about, say, planets like hot Jupiters spiraling into their stars, I mean, there are various mechanisms of like tidal forces. You've got things, you've got accretion disks that things are moving through. I mean, all of these have been suggested.
Mm-hmm. Yeah. So, yes, there are other suggestions, because there are not only gas in the vicinity of the supermassive, not only stars in the vicinity of the supermassive black holes, there can also be gas And the black holes may also have accretion disks that can interact with each other in non-trivial ways. So all these things have been considered, and of course, they're very hard to model at these extreme environments, right? So it may still be, again, that we're missing some of the key ingredients in our simulations and in our calculations that show that the combinations of these effects are actually enough. But what our current kind of knowledge and calculations tells us is that it doesn't quite seem to be enough to make all the black hole merge.
It's super tankers going through clouds of tiny bugs, except far more ridiculous.
That's right.
Yeah. Okay. Mm-hmm. All right. Well, then let's get to your paper then. So what are you proposing?
Yes. So what we're proposing is that, at the center of the galaxies, there is indeed gas, stars, but something that we think is very abundant there too is dark matter, right? And we often kind of forget about it because it only interacts gravitationally. We also don't exactly know the properties, like we know very little about how it's distributed at the center of the galaxy, so there are uncertainties, right? And one of the main reasons that people had not considered seriously the effect of dark matter so far is that, so we know that the supermassive black holes moving through the dark matter just through purely gravitational interactions can slow down the supermassive black holes. So that was known via this effect called dynamical friction. Essentially is something very similar to, say, if you have a bowl of water and then you're moving a spoon through it, right? You feel some friction. In this case, it's similar to that, but just through purely gravitational effects. But the problem is that these black holes are so massive that if you think about this bowl of water, they would make all the water splash out of the bowl very quickly because, they're so heavy, right? So people thought the same would happen with dark matter. It will just be expelled and dispersed from the central region of the galaxy very quickly, and they could not really impact the orbits of the supermassive black holes in a meaningful way. So the new thing that we're proposing is that dark matter may have something that we refer to as self-interactions. And the way to understand kind of it is that, instead of water, dark matter may be something more like honey, like with more viscosity to it, right? Such that when the black holes are moving around, it's harder for them to push all the dark matter away, right? So you solve this issue of the black holes expelling off all the dark matter if dark matter has self-interactions.
Now, the observations of dark matter, sort of most famously things like the bullet cluster, but just the gravitational lensing that's been done to find dark matter. I mean, the main impression that whatever this particle is, it doesn't have a cross-section, doesn't interact with itself. Mm-hmm. So is this non-interaction with itself, this doesn't matter, it can still interact with a black hole through something other than gravity?
So it's a quantitative matter here. So we know that dark matter doesn't interact with itself too strongly, right? But of course, we cannot tell exactly, the self-interactions may be kind of small enough to not affect things like the bullet cluster, but maybe strong enough to affect the merger of the supermassive black holes. And this is indeed what we're saying. The values for the self-interaction cross-section that we see have a significant impact on the motion are just slightly below current constraints, which we think is exciting because, they're close to what we know cannot exist, which means that if we improve observations of, you were saying, systems like the bullet cluster or observations of the distribution of dark matter in dwarf galaxies and other galactic systems, we may be able to find this self-interaction strength that we think can help solve the final Parsec problem.
So how would you search for observational evidence that this might be the way?
Yes. So I think there are two things. The first one is the one that I was discussing, maybe correlate with some of the other environments where we can test dark matter self-interactions, because indeed there are some people that argue that some of the observations of the dark matter distribution in galactic systems are better explained with dark matter self-interactions. And the other one is looking at the data that we have from supermassive black hole mergers. And that is the gravitational wave signal that they're emitting. Because very excitingly, last summer, the pulsar timing array collaborations observed a signal that is compatible with the gravitational wave emission that we would expect from all the supermassive black hole mergers across the history of the universe, right?
Right. So once again, I mean, we have observational evidence that these mergers are happening, and obviously that's exciting because you might have to come up with a completely different explanation for how you get supermassive black holes in the first place. But now, okay, they are merging probably. So now the question is, how are they overcoming the final parsec problem? So I want to go back to those observations that you mentioned. So I guess what would it look like in the signal if black holes were either in the process of merging or were far enough away from each other, but they were, I guess, dark matter was interfering with the merger process?
Exactly. So the signal that we have is basically telling us how strong the gravitational wave emission is at a given separation for the supermassive black holes. Right, and just assuming that the signal indeed comes from the mergers, right? So in the first place, you have to assume that supermassive black holes do merge sufficiently fast to generate the signal, right? So you have to have solved the final parsec problem, and then you can look for small imprints on the signal of this agent that's kind of making the black holes merge. And so what this would look like is that when the black holes are very close together, gravitational wave emission overwhelms everything. But when they're at like some intermediate distance, we know that part of the energy is going into gravitational waves and part of the energy is going into friction or whatever is slowing them down. And this is something we can observe in the signal. We can observe like how much that the signal corresponding to the black holes at these separations where we know there has to be something else has to be showing this kind of deficit in power in the gravitational waves because the power is going into friction.
Right. And is this something that, I mean, right now, LIGO, Virgo, they're not capable of detecting supermassive black hole mergers. The hope is that LISA will be able to make those observations. So you're talking about observations from LISA, or do you think there's a version of that would be visible in things like LIGO?
Actually, I'm not even talking about LISA right now. I'm talking about pulsar timing arrays. So,
oh, really? Okay.
Yeah. So these are because LISA can see supermassive black hole mergers, but it's better at looking at intermediate mass. Whereas the ones we're looking at are huge, like masses of 1 billion times the mass of the sun. So they're the very largest supermassive black holes that we have. And those are the ones that can be seen with pulsar timing arrays, right? So maybe Lisa can tell us something about the black hole environments, but we're now talking about directly the data that's already there from pulsar timing arrays.
And the thing that's kind of really interesting about the pulsar timing arrays is just every year that data gets nicer. It gets better year after year after year. I mean, we're at whatever 15 years with nanograv and there's other observations. And so do you think that data is already in the observations, or do you think that improvements to the pulsar timing arrays would need to be made to be able to see that signal?
So there is some evidence in the data for the presence of this signal, and maybe also for this lack of power at small frequencies, which corresponds to like large separations. There's still a hint, but as you were saying, the data is still noisy, not precise enough to really tell. But the exciting thing, as you're saying, is that these collaborations like Nanograph and the collaborations in Europe, Australia, and China are still connecting data, and it's only going to get better with time. And most excitingly, there's the new radio observatory being built called the Square Kilometer Array that will really improve the sensitivity, right? So if the signal that we think we're seeing with current pulsar timing array observatories is indeed there, the Square Kilometer Array will really pin down pin it down with a lot of exquisite precision.
Now, when you say this signal that you see or you think that you're seeing, can you give us a sense of your uncertain? Like, how many sigma are you talking
so I think
about here?
the current evidence for the signal is around 2 to 3 sigma. So it's still, as I was saying, this is a very, very difficult analysis because they're looking for a very particular kind of noise in the arrival times of the pulses from pulsars, right? And there are many things that can contribute to slight variations in these arrival times. So one has to be very careful that one picks out the collaborations, very careful to look for this exact pattern that one would expect from gravitational waves. They're constantly improving. They're constantly gathering more data.
And the square kilometer array, we're still half a decade away from it coming online. Is it like orders of magnitude better in measuring the signal of the pulsar timing array?
Not only that, but it will also be able to observe way more pulsars, right? And in a game where statistics really matter, that also really helps you with improving your signal.
And so you feel that once you get those observations, then you should be able to know once and for all if this interaction with dark matter is leading to the merger of the black holes.
So we have also work to do on our side to really know, because the analysis that we have done so far is kind of an analytic calculation that cannot fully capture all the possible environments that black holes merge in at different redshifts and for different masses. So we're currently working on refining our predictions. So it will be a combination of development or of our theoretical predictions and improvement of the data that will allow to tell.
It's funny because when I think about this, I'm actually less interested in how to make black holes merge and more interested in what this tells us about dark matter as a thing that is helping to make black holes merge. So what do you think? Like let's say that the square kilometer array is online. You've gotten really good data for the signal is unambiguous that this interaction is happening and this is what's causing the black holes to come together. What does that tell you about dark matter?
I agree. Then things get really excited, because if we can really pin down that dark matter is there, dark matter is the thing that we can see, then we can say a lot about what kind of self-interactions dark matter have. Because we're finding that the exact velocity dependence of the self-interaction cross-section, basically how strong the interactions become when dark matter is moving faster and faster or slower. So it's so we're finding that the final parsec problem being solved is very sensitive to how that works. And that can be connected with the particle physics model that basically explain what the microscopic origin of the self-interactions are. So we could potentially really use these observations in order to learn about the microphysics of dark matter. And I agree that's, once we get there, and if we get there, that will be very exciting.
When you think about the various candidate particles for dark matter, sterile neutrinos, axions, something else, which ones then seem more likely to you, and which ones you could maybe rule out through this level of self-interaction?
Right. So the kind of models that we're thinking of are kind of similar to traditional WIMPs, but with a self-interaction. So we don't really know we cannot really tell what the mass of the dark matter particle is. What we can tell is, this force that generates the self-interactions has to be mediated by some other particle, right? So what we can fairly precisely say is what's the ratio of the mass of this force mediator to the mass of the dark matter particle.
And similar to, say, the search for the Higgs boson, like you're looking for the force mediator particle in your large hadron collider. So would you then be able to sort of provide a number to particle physicists and say, look for this?
I think not a generic number, just because what we're sensitive to is not any interactions of the dark matter particle with normal matter. It's just interactions of dark matter with itself. So we cannot, and that's not necessarily connected to the strength of the interactions between dark matter and normal matter, which is what we care about, like to look for these particles in the LHC, in colliders, or in dark matter detectors. However, once one has in mind a specific model and a specific way that this dark matter was produced and how the self-interactions play into that, one may be able to kind of narrow down in what the strengths of the interactions with normal matter may be for everything to work.
Now, I mean, with mergers between black holes, that's going to be one place where this dark matter is showing its face. But there were probably lots of other ways across the universe that you could make large-scale observations. When you think about the Roman telescope coming online, Vera Rubin, Euclid is already launched. I mean, there's a lot of really interesting tools that have just come online to be able to do searches for large and small scales. So are there other places where you might look for that signal?
Yes. In particular, I think the kind of these self-interactions would have a significant impact on the distribution of dark matter in small scales. So that's where we want to look. Things like dwarf galaxies and systems that are overdense in dark matter compared to normal baryonic matter. Then these are the systems that may get affected by the existence of the self-interactions. So indeed, people are, for instance, with JWST, starting to see many more collisions of galaxy clusters, things like the Ballet cluster, right? So those are places where we could also see a hint of the existence of the self-interactions.
Right. So what if you're wrong? What would you be seeing to make you go, oh no, that was just a statistical improbability, and it turns out that we were wrong? What would be giving you that signal?
So I think the main thing would be, if one looks at the signal and you find that it doesn't really correspond what we were expecting from dark matter friction, then I guess the logical conclusion would be, well, it's not dark matter, or there's something else that's way more effective at solving the final Parsec problem and overshadows, if you wish, the effect of the dark matter. Of course, that would be exciting, right? Because this would mean that there would be some other astrophysical player that's really having an effect. So that's interesting. So I think even a negative result is an interesting result. We would be ruling out dark matter as an effective agent in solving the final Parsec problem, meaning that we'd have to look for something else.
Right. But I mean, you're detecting that signal in the interactions, the mergers between these supermassive black holes, but there must be other factors that you could also detect other signals during this merger process. So it's like, how do you know it's the dark matter and not just, a whole bunch of stars lined up nicely doing gravitational assists?
I agree. So I think in terms of observations, it's not easy. There's one I can think of, and is that, we can look around us in the galaxies that we see and their active galactic nuclei, so the very centers, and try to deduce what's sitting there. Is it really just a single supermassive black hole at the center, or maybe a binary pair that's orbiting at some distance, right? So one could think of, and people are doing surveys of these active galactic nuclei, and see as a function of the environment and as a function of the mass of the supermassive black holes, how many binaries we find versus single supermassive black holes. Then, I expect that distribution of binaries versus single supermassive black holes would be different depending on what's the agent that's making that merge. So that's another way that we could look, in addition to the gravitational waves, at what could be there solving the final Parsec problem.
So what if through observations with Webb and the pulsar timing array and LISA and things like that, it really doesn't feel like supermassive black holes are able to have merged quickly enough to form the size of the black holes that we're seeing earlier and earlier in the universe. What other mechanisms do you think are plausible for how we got such big black holes so early?
Mm-hmm. So there are two main things. The other way that the black holes can grow is through accretion. So they can accrete gas. Maybe that process is more effective than we thought and can help them grow faster than we thought. The other possibility is that maybe the supermassive black holes were born already very massive, way more massive than we were expecting. And there's indeed some hints from JWST that may be the case, because we see supermassive black holes that are already very large and very high redshift, so very early on. So this means that they either were born already very large or they were very effective at accreting gas very early on. So that could be a way how you would get these very large black holes. But I think this is not, this would not be telling you that black holes do not merge, because we know that galaxies do merge, right? So there's always the question of what happens to their supermassive black holes when the galaxies merge. So that's a question you still have to answer.
And the pulsar timing array is telling us that black holes merge.
Yes, so, of course. Yeah, as
so we know this is happening.
Well, we know that there's a signal. There are still some other potential kind of more exotic explanations for this gravitational wave signal that we cannot completely rule out, of course, at this moment. It may still be that, the supermassive black holes, so this gravitational wave signal is coming from something else. And then we have to think about a bit more about to what extent the final Parsec problem needs to be solved.
But I wonder about these. I mean, with a black hole accreting gas, I mean, there are limits to the Eddington limit. There's a limit to how much a black hole can draw in gas, and people have done this math and said we can't get a black hole to accrete that much gas and become that big. So you mentioned maybe they started out bigger. So what would that look like? What would sort of be the cause of that?
Yes. So kind of the leading explanation or possibility to form very massive black holes to begin with is a scenario that's called the direct collapse. So the idea is that very early in the universe, before forming stars or anything, we have huge clouds of gas that start to cool by emitting radiation, and then they become denser and denser. So what usually happens is that if this cooling is very fast, instead of the cloud just collapsing on itself, at different sites, it forms separate sites where like some granules where things collapse and form stars. But if cooling is slow, and this is very tricky to engineer because it depends a lot on the chemistry of the gas, what different elements you have there. If cooling is sufficiently slow, then the cloud may just collapse into a single object, a single very massive object that would make up a very massive black hole. So that's a way how astronomers think very, very massive black holes could have been born very early on.
Right. And the kinds of limits that we have in star formation today, that comes from the pollution of the heavier metals. But in theory, the more pristine hydrogen, helium early on could lead to these much larger objects. But it just depends on how you can manage the temperature in the gas to keep it all together.
Exactly what cooling channels are at play. So it needs like current calculations show that one needs a very fine balance in order for this direct collapse mechanism to work.
And then I guess another possibility is primordial supermassive black holes.
Yeah, that's a good point. That's another possibility. Maybe the black holes that we're seeing are not coming from from astrophysical origin, from dying stars or the collapse of gas. Maybe they were already there since inflation or very early on. Yeah, that's another possibility. Mm-hmm.
Do you think that, like, with the pulsar timing array, with LISA, with other, let's say we make the super duper Einstein telescope or the Big Bang observer, like some really big gravitational wave observatory, could we get to a point that we could rule out various mechanisms of how those first supermassive black holes formed?
I do think so. I do think so, yes. And one of the main ways, one of the ways that we could rule out, for instance, the existence of primordial primordial black holes, or find evidence for them, is if we find black holes of masses that we know cannot form astrophysically, right? So they're because we know there's a limit. If a star is too light, it will not form a black hole. It will when it dies, it will form a white dwarf, a neutron star, but not a black hole. This means that if we find black holes of, say, less massive than a solar mass or so, then it's very hard to find an astrophysical origin for them, meaning that they're likely primordial in origin.
I was more thinking about the sort of mechanisms for those supermassive black holes, still in astrophysical methods, but to have the direct collapse. Like, what would it take to get us to direct collapse is the way?
So I guess if we understand better the conditions of the gas at these very early times, then we may be able to really tell whether this direct collapse possibility is actually possible to realize or not. Yes. Another way that one could think is that, if these supermassive black holes are indeed of primordial origin and were there very early on, then they may have had a lot of time to accrete matter around them, and in particular dark matter. So if we have a way of probing, the environments of these supermassive black holes, which we may be able to do again with gravitational waves observations from LISA, if we find huge overdensities of dark matter around them that could have only formed if these black holes are very, very, very old, or they're are of primordial origin, then this may be some evidence or some way of testing this possibility.
Right. Gonzalo, what are you obsessed with right now?
Well, more and more, I'm getting obsessed about these gravitational wave probes of black hole environments, right? Because these environments are very, very interesting for astrophysical purposes to understand how gas accretion works. But now we're saying that these environments will also be very interesting to understand how dark matter works, right? So I think it's just so exciting that there's going to be so many new gravitational waves observatories that will help us understand what the environments of the supermassive black holes are, that it really opens like a lot of possibilities and to really understand physics and astrophysics, and also hopefully, because that's what I care most about, the nature of dark matter.
Yeah. It's amazing that we've only detected gravitational waves for less than a decade. What, 2017, 2015? Anyway, not long. And yet we already know of dozens of mergers, supermassive black hole mergers, and LISA is coming, and as you said, the square kilometer array is coming. There's all these interesting ideas in the works to take this to the next level. An idea that was once thought almost impossible now is becoming a new routine tool that astronomers can use to perceive the universe. Amazing.
Yeah, it's amazing. It's as if you just started to detect visible light 10 years ago, and now you're able to also see radio, to see X-rays, to see all kinds of frequencies. So suddenly, like, the whole universe is lighting up in so many different frequencies and gravitational waves. Yeah, I find it extremely exciting.
Yeah, absolutely fascinating. Well, Gonzalo, thank you so much for taking the time to chat with me today. Good luck in solving the final parsec problem and discovering some characteristics of dark matter. That sounds great.
Yeah, thank you. Thank you for having me.
I hope you enjoyed this conversation with Dr. Álvarez. I'm going to give you some of my thoughts in a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chipolin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. This was a very exciting interview for me. It brings together a bunch of big questions that I have about supermassive black holes merging into one another, and of course, the nature of dark matter, which we have spent a lot of time thinking about. And when there is this detectable signal of the dark matter that is starting to slow these black holes down and help encouraging them to merge, that's like another data point for learning more about dark matter itself, as well as supermassive black holes. We might not know what dark matter is, but the more people can constrain its behavior, provide information to the particle physicists for the kinds of experiments that they should be running to be able to find this kind of thing. And so I love when you have these big observational programs that are searching for something out there in the universe that can then give really useful information to other physicists that are trying to understand just like the base nature of reality. So, a very fascinating conversation. I hope you enjoyed it, and we'll see you next time.